Welcome back, everybody. So we're going to continue on using the frequency table that we created earlier to kind of talk about things like class width and tolerance in this case. So first of all, class width is just the width of all of your individual classes. Now there's a couple ways you can find class width, and which one you're going to use is going to be very dependent on what type of data you have. For example, if you have all of your raw data, but you have no table and you have to create it from scratch, you're going to have to do a very different approach than if you were to have a partially filled out table or even a completely filled out table. So first of all, let's define what the class width is. Class width is just the width of your initial intervals, your classes. So in this case, from 3 to 8, what is the width of that class? Now, this is extremely important because one, we'll use it for other parts later, but two, this is actually one of the first things a lot of students will get incorrect whenever they're doing these problems. So let's define what class width is. So let's determine how do we find that class width. So let's actually figure out how do we find those class widths based on the type of data and or table that we have. So the first way is that we can find our class width by taking the upper class limit minus the lower class limit and then adding something called tolerance. So the first way is going to be, we're going to take our upper class limit, I, actually let's do K to represent our class limits instead of our individual data points, minus the lower class limit for group K, and then once we've subtracted that, we are going to add our tolerance. Now, this is where most students actually get it incorrect. So let's say that we take this interval right here, 8 and 3. Our upper class limit is just this right interval number of our interval. So this would be the upper class limit for group 1, and this would be the lower class limit for group 1. So in this case, it would be 8 minus 3, which would give us 5, plus our tolerance. Now, what is tolerance? Tolerance is just the distance from one interval to another. So in this case, our tolerance T is equal to 1. Now, most examples you see are going to have a tolerance of 1, and most things that you will have are going to be a tolerance of 1. Now, what determines your tolerance? Well, first of all, if you have a table like this, your tolerance is just the difference from your upper class limit of one group to your lower class limit of the next group. So for example, here from 8 to 9, you have a distance of 1, meaning you have a tolerance of 1. So in this case, we would just add 1 to this and we would get a class width of 6. Now, what about if you have a different tolerance? Well, your tolerance, let's say you have the data, so you don't have a table where you can quickly, easily figure out what your tolerance is. If you have the raw data, it's going to be based on the type of data you have, the numbers. So if you have whole numbers, let's say you're counting how many cars park in the garage over some given time. So let's say Monday, you get 63 cars parked in the parking deck. Next day, you get 84. Next day, you get 22. Next day, you get 76. Well, in this case, you have all whole numbers. So if you have whole numbers, then you would have something like 90, 76, 82. Then you're going to have a tolerance of 1. If you have a single decimal point, let's say it was your possibility is like 90, 90.1, 90.2. Because these have one decimal, these will have a tolerance of 0.1. Let's say that this could be something like if you have a digital thermometer and it does temperature in for 0.1 degrees. So you could have like 70 degrees Fahrenheit, 70.1 degrees Fahrenheit, 70.2 degrees Fahrenheit. In this case, it's the gap between your possible numbers, or a tolerance of 0.1. But let's say you have a better digital thermometer, and yours does 2 decimal points. Let's say you could have like 90.00, 90.01, 90.02. These are just possibilities. Then in this case, because you have 2 decimals, the difference between any given possible value is 0.01. So this would have a tolerance of 0.01. Now this goes to any degree. So for example, if I have 3 decimal places, it would be 0.001. If I have 4 decimal places, it would be 0.0001. if my data points can only be in terms of tens. So maybe it's something like 10, 20, 30. These are just possible values, by the way. 40, so on and so forth. If there's only a difference of numbers of 10, meaning I don't have any values between, maybe I'm rounding something like this, then in this case, the tolerance would be 10. So your tolerance will be based on the actual data. Now, if you have the table, it's super easy because you just figure out what the gap is from your upper class limit of one group to the lower class limit of your next group. So in this case, though, one way we can find class limit, if you already have part of a table filled out with a lower class limit and the same group's upper class limit, you can figure out what the tolerance is, then you can figure it out by taking the distance between this group, so upper class limit minus lower class limit, plus your tolerance. The second method we have is that we're going to look at the difference between two consecutive lower class limits or upper class limits. So the second way is that we could take, for example, the upper class limit for group 2 minus the upper class limit for group 1. Or we could take the lower class limit for group 2 minus the lower class limit for group 1. So for example, our upper class limit for group 2 here is 14 minus our upper class limit for group 1 is 8. So 14 minus 8, we get a class width of 6, which matches what we just had using our other method, our first method. Same thing with the lower class limits. If I do lower class limit 2, that's going to be 9, minus lower class limit 1 is going to be 3. This will give us 6. So this is one way you could do it. The next method we have, now this is for if you have raw data only and you're creating a table from scratch generally. But the third method is that you want to take your largest value of all of the data that you have. You want to subtract the smallest value, and then you want to divide by the number of classes. So in this case, we take our largest value, which in this case would be 26 probably, minus our smallest value, which would be 3, which would give us 23 at the top. Divide by how many classes you have, 1, 2, 3, 4. This would be, of course, based on if you had the data, you would determine how many classes you want. For this class, we're going to tell you. For example, when you're doing your homework, it might say you have 6 classes, something like that. And this will allow you to get whatever your class width is from your raw data. So let's actually do that real quick. Let's do 26 minus 3 divided by 4. So if we do 26 minus 3, that's going to give us 23. So 23 divided by 4 is going to give us 5 point something. Now, when you're doing your class width this way, here's the thing. Whatever you get, you always round up. That means that if you get a class width of 5.9, you would round it up to 6. If we got a class width in this when we got 5.2, you would still round it up to 6. This is because, remember that second rule, we need to make sure that our histogram is exhaustive, meaning that it is better to round up and make sure you have extra interval so that everything falls in your interval than to round down, because if you round down, what's going to happen when you create your frequency table, your last value, your biggest values are probably actually going to fall outside that interval. So what you're going to do with this is you're always going to round up. Now, one thing I want to clarify on this, because again, this is one of those confusion points sometimes students have. This rounding is going to be based on those types of numbers you have, or your tolerance. So if you're using whole numbers, you round up to the nearest whole number. In this case, 6. If you have 1 decimal, you round up to the next single decimal. If you have 2 decimal points, you round up to these next second decimal. So for example, if I have 2 decimal points and I get 5.036, I would round up to 5.04. So when I say round up, it is based on the type of data you have, or the tolerance. So your tolerance also can help you determine how do you round these class widths. Now, let's say that we did this method and we wanted to create our table. So we have a class width of 6, and we want to start with our smallest number. So what you do is you start with your smallest number, 3. And then we need to figure out what is the next number in that interval. So we need to get our upper class limit. So the way you're going to do this is you are actually going to take your lower class limit. Your upper class limit is going to be equal to your upper class limit plus your class width minus your tolerance. So in our case, our upper class limit is going to be our lower class limit, our starting point of 3, which would be the smallest point of your data, plus our class width of 6. If we just stopped here, what's going to happen? 3 plus 6 is going to give us 9. But we know, because we've already filled out this table, that this should be 8. And it's because we actually have to subtract our tolerance, which in this case is 1, which would give us an upper class limit of 8. Now, a couple things about this. If you wanted to kind of get an example of why this is the case, it's because when we count these intervals, we have to start from the starting point. So for a small interval like this, it's really easy. We'll just count on our fingers. Starting at 3, 3, 4, 5, 6, 7, 8. Notice when we go up by 6 for our class width, starting at 3, we ended at 8. Another thing I wanted to briefly talk about before we move on to this and fill out the rest of this piece by piece is when you are doing this third method, we actually have a term for this here, the largest value minus the smallest value. This is called the range. Which we usually just write as a capital R. And I know my handwriting's bad, but the bottom just says classes. I just wanted to keep it consistent. So this is actually called the range. So anytime you are asked to find the range of something, it just means take the largest value, take the smallest value, subtract the smallest from the largest, and it tells you how much distance there is in between all your data points. Right? You're taking the extreme ends of both your data, and then you're seeing how much distance there is between them. So going back to filling out our table, now that we've gotten our first interval, 3 to 8, what do we do next? Well, now you go up by your tolerance. So in this case, our tolerance was 1, so our next value is 9. And then again, we could add 6 minus 1, which is 5, which would give us 14. Or if it's a small interval like this, just count it out. So it'd be 9, 10, 11, 12, 13, 14. Go up by 1, you get 15. Again, 15, 16, 17, 18, 19, 20. Go up by our tolerance, 21, and then 21, 22, 23, 24, 25, 26. So you'll notice that we got the same table that we originally had by rounding our value. Okay, so next thing is, what about if you have a partially filled out table? So let's say you had this table, but you didn't have everything filled out, and you don't have the original data. Well, this is where you could use the other class width methods. Let's say that I gave you a table that looks like this, or your classes that look like this. Well, in this case, I could figure out my class width by taking the upper class limits and finding the difference between them. 20 minus 14 is equal to 6. Or I could use my lower class limits. 21 minus 15 is 6. Or I could use this single interval that I actually already have, right? 20 minus 15 is going to be 5 plus our tolerance. Now, if you look at the slides that we have with this video, you'll see in the top right corner, we have this data, this table here. And because all of our numbers are whole numbers, and because we also see the table is filled out already, we can easily see that we have a tolerance of 1, because we have a gap of 1 between 8 and 9. And also because they're all whole numbers, we know the tolerance is equal to 1. But because we don't have the original data, we would have to use the table for it. But if you have the original data and the values were something like 3, 7, 22, things like that, we would know the tolerance is 1. In the table on the bottom right, table 2, you'll see that we have values that go from 0.2 to 0.7. Second group is 0.8 to 1.3. Third group is 1.4 to 1.9. Fourth group is 2.0 to 2.5. In this case, because our data points are based on single decimals, that means that we would have a tolerance of 0.1. Great. So now we've talked about briefly that our lower values for each interval are our lower class limits. So this 3 would be lower class limit 1. This 9 would be lower class limit for group 2. This 15 is our lower class limit for group 3, and this 21 is our lower class limit for group 4. Our upper class limits are the larger values of our interval. So this 8 is our upper class limit for group 1. This 14 is our upper class limit for group 2. This 20 is our upper class limit for group 3, and 26 is our upper class limit for group 4, or interval 4. Now, the reason I keep repeating this is because this is, again, another one of those places where students commonly make mistakes. And this is because when we have these gaps in our data, these are class limits. Now, in a minute, we're going to talk about when we close these gaps, we will be replacing them with class boundaries. And so you might get a question that says, what is the lower class limit of group 3? And you would say, okay, it's 15. Where you might have another question that says, what is the lower class boundary of group 3? And if you put 15, you will get the answer incorrect because that is the lower class limit, not the lower class boundary. Okay, so now let's talk about midpoints. So do you remember how I said, in this interval, if I don't have the raw data, I don't know what the values are. So I have, for example, 2 data points, which are between 3 and 8, but I don't know what they are. They could both be 3, they could both be 8, one could be 3 near, and one could be near 8, they could be in the middle somewhere. These 7 values, I have no idea what they are. I just know that they're somewhere between 15 and 20. So oftentimes what we'll do is we will actually use the midpoint to represent the average of that group, which we'll use to represent that group. So to find midpoint, what we're going to do is we're actually going to take the average of our group. So in this case, we're going to take the average of 3 and 8. So we have 2 data points, so it's going to be our lower class limit, I, plus our upper class limit, I, and then this is going to be divided by 2. So for our first group, this would be 3 plus 8 divided by 2. Now, 3 plus 8 is going to give us 11, divided by 2 would give us a midpoint of 5.5. So this means that if we were to fill out the rest of this table real quick, I'll do it down here. Let me fill this out. I'm going to put my midpoint here. I'm not going to do the frequency yet. This means that my midpoint for my first group is 5.5. Now, going back, do you remember with our initial description of our histogram that we wanted everything to have an equal class width? Well, guess what? This is one of those advantages, because if all of my classes or my intervals are the same width, this means that I can actually figure out what the difference is from my lower class limit to this midpoint, and it's always going to follow a pattern. So this 5.5 is 2.5 higher than 3, which means I can do the same thing here. 9 plus 2.5 gives me a midpoint of 11.5. 15 plus 2.5 gives me a midpoint of 17.5. And 21 plus 2.5 gives me a midpoint of 23.5. And this is, again, I told you that there was some advantage to it. By them all having the same width, we actually can find a pattern to very quickly fill this out instead of figuring out the midpoint for every single class. Now, you can do that. That's perfectly fine. And you might want to do it just to make sure. If nothing else, if you're pretty sure they're all the same width, maybe just check the last one to make sure that you don't have an open-ended final width. Now, for this class, we generally don't, because what do you do for the midpoint in that case? If I have something like 80 plus, do you put it 90? Do you follow the same trend? It gets kind of complicated whenever you have that open-ended group. Okay, so now let's talk about our class boundaries. So looking at our data we have here, we go from 3 to 8, 9 to 14, 15 to 20, 21 to 26. And we've got these gaps, or our tolerance of 1. So to actually create your class boundaries, what we're going to do is we're going to take our lower class limits, and we are going to subtract 0.5 times our tolerance. And we're going to take our upper class limits, and we are going to add 0.5 of our tolerance. So what does this mean? Well, if we look at our lower class limit of 3, we're going to subtract half of our tolerance. Well, our tolerance is 1. So that means that our first lower class boundary would be 3 minus 0.5 or 2.5. So if I were to draw this out, this is the same thing as we're going to go to the left by 0.5. So we get 2.5. For this one, we go down, we get 8.5. For group 3, we go down, we get 14.5. For group 4, we go down, we get 20.5. So we do that for every lower class boundary. So this is going to be 8.5, 14.5, and 20.5. Now, I want to caution you, remember, this is half of your tolerance, meaning if you have a tolerance of 0.1, then you should be subtracting 0.05. If you have a tolerance of 10, you should be subtracting 5. So generally our tolerance is 1, but it's not always. So don't always subtract 0.5. It's 0.5 times whatever your tolerance is. So now with our upper class boundaries, what we're going to do is we're going to add half of our tolerance. So we're going to go to our first one, 8, and we're going to add 0.5 and get 8.5. For second group, 14, we're going to add 0.5, get 14.5, 20.5, and then for our last one, 26.5. So our upper class boundaries are going to be 8.5, 14.5, 20.5, and 26.5. So basically all we've done is we've taken the gap between our upper class limit of one group and our lower class limit of the next group, and we've gone up by 0.5 on our upper class limit, and we've gone down by 0.5 of our tolerance on our lower class limit, and we've brought them together. And now you'll notice there are no gaps. There's nowhere that our data could fall on this where it is not accounted for. Because remember, we have to have no gaps because our interval must be exhaustive, meaning it must be continuous from our starting point to our end point. Now you might wonder, but why do we expand out to left and right? Because we know that our data falls within this interval. And this is because, again, we want to keep our class widths the same. If I expand this interval by minus 0.5 and plus 0.5, and this one by minus 0.5 and plus 0.5, but this one I only expanded by plus 0.5, I now have a different interval length for that first interval. Same thing at the end. If I only subtract 0.5, but I don't add the 0.5, I've changed the width of this interval. So this is the reason why we do it for the entire thing. So every group is basically, you have an interval and you are expanding out by the entire tolerance. Half of it to the left, half of it to the right. So now we have our class, our midpoint, our lower class boundary, and our upper class boundary. And this is not even counting with our frequency. And in fact, this is what you would need to set up your histogram. Because if we were to set our initial x-axis for our histogram, our title here, histogram, our x-axis is going to be either based on our midpoint or based on our class boundaries. So for example, if we're using our class boundaries, it would be 2.5 to 8.5 to 14.5 to 20.5 to 26.5. And then what we would do is based on our frequency, let's say we're doing a frequency histogram. We just look at our frequency here. It looks like we go from 2 to 7. So let's say we do groups of 2. So this is going to be our class boundaries. This is going to be our frequency. So we have, this is going to be like 2, 4, 6, 8. So what we do is you just go up to whatever height you have. So in this case, our first group has a frequency of 2. And you go from the lower class boundary to the upper class boundary, and you create your box, your rectangle. The second group, we go up to 6. For the third group, we go up to 7. And for the fourth group, we go to 5. So with this, we can already make our first histogram. We got our title, we've got our x-axis representing our class boundaries, we've got our y-axis representing our frequency. Now remember I've talked about scale before. Your scale is going to oftentimes be related to specifically your y-axis because you're going to want to base that on your frequency. So this is a regular histogram or a frequency histogram. Now I mentioned you could also use the midpoint. Oftentimes when we have a group of data and maybe we don't know exactly what the values are, but we want to represent the data in terms of whatever that middle point is, which we oftentimes will do, right? So think about like when you're looking at clothing sizes. They don't have every possible clothing size. What they generally do is they pick the middle of an interval and we'd put our midpoint. So instead of having our boundaries, we would actually label the groups by our midpoints. 5.5, 11.5, 17.5, and 23.5. And that way we can kind of think of this as the 5.5 group, the 11.5 group, the 17.5 group, and the 23.5. Because remember, our midpoint is the average of that interval, right? So if I don't know what the values are, then the best guess I have is that on average, they would be 5.5, 11.5, 17.5, and 23.5. Okay, so now let's expand our table a little further. So let me just add my frequency real quick. This is going to be 2, 6, 7, and 5. So our class frequency is just the number of data values that fall into that particular class. So if you have raw data, then when I'm looking at that raw data, let's say I get a 4, I'd say, okay, 4 falls into this group. I would probably, if I didn't have the numbers here, I would put a tally. And let's say the next data point was 11. So 11 falls into this group, put a tally. Let's say again, the next one is 10. 10 falls in this group, put a tally. Next data point is 7, put a tally. And then basically I would just tally this out until I get whatever number I have. And then I would just write down that number. So this is how you get the frequency if you have the raw data. If you already have a table filled out, then you don't have to do this step. Now, a lot of times if you have a partially filled out table, what you might find is something like this. You might have the table where you've got your 2, 6, and let's say 5. But what we're going to do is we're going to also include the total. So we have a total of 20. Well, your frequencies have to add up to this total. So if I had this one left blank, then this would mean that I've got 2, 6, and 5. So if I were to add those up, that adds up to 5 plus 6 is 11, 12, 13. So that means that I know that it has to add up to 20, meaning that this has to be 7. So I could actually figure out what is missing from the table using this total. The next thing is we're going to talk about relative frequency. So relative frequency is going to be the frequency for the group that you're in, so frequency I, divided by sigma f sub I. Now let's talk about a few things. First of all, if you remember that I represents an index, so it's saying frequency of group I. So F1 would be the frequency of group 1. F2 would be the frequency of interval 2. F3 would be the frequency of interval 3, and F4 would be the frequency of interval 4. This symbol here, this is called a summation. The Greek character capital sigma. And all it means is add up the values. So really what this means is add up all your frequencies. So in this case, it would be frequency of group 1 plus group 2 plus group 3 plus group 4, or the total of your frequencies, which is why we like to write our total here. So in this case, our relative frequency of the first group would be the frequency of the first group divided by the total of the of all the frequencies. So relative frequency 1 would be 2 divided by 20, or 0.1. So for our relative frequency, we could have it as 0.1. Now, a lot of times, though, you are actually going to see this in a different way, which is you might see something like this, parentheses, percent. That just means that they want the data in terms of a percentage. So if that's the case, if it's in terms of percentage, all you do is you take your value and you multiply it by 100. So in this case, 0.1 times 100 would give us 10, or 10%. Okay, next one, 6. 6 divided by 20 is going to be 3 over 10, or 30%. 7 over 20 is the same thing as 3.5 over 10, or 35%. And the last one, 5, is going to be a quarter, so that's going to be 25%. So these are our relative frequencies. Now, if you want to double check yourself to make sure you're on the right track, if you add up these relative frequencies, they should sum up to either 1 if you're using decimal, or sum up to 100 if you were doing by percentage. So in this case, 10 plus 30 is 40%, 50, 60, 75%, 100%. That means that we didn't miss anything. Now, when you're doing these calculations, let's say you're using a scientific calculator and you're rounding to some decimal places, you may not get exactly 100%. You might get like 99.98% or 100.02%. In that case, it's probably just rounding error because of how you rounded when you did these calculations. Because you might get some repeating decimal like 0.3333 on forever, and then when you round it to 0.33, you're missing that little bit. And if you do it for a couple, you might be off by just a smidge, but in the end, it does need to sum up to 100% or 1. Now, what does this relative frequency actually represent? This represents the proportion of this group to the total. Meaning, for example, like let's say that these 4 groups, don't worry about the classes, let's say these 4 groups are the quarterly earnings of a company. So our frequency would be how much money that company earned during a quarter. So frequency 2, let's say it's millions of dollars. They earned 20 million in the first quarter, 6 million in the second quarter, 7 million in the third quarter, 5 million in the fourth quarter, for a total of $20 million this year. Relative frequency would tell how much did they make as a percentage of the total in that quarter, meaning that the first quarter accounted for 10% of their earnings. The second quarter accounted for 30% of their earnings. The third quarter, represented 35% of their earnings, and the fourth quarter represented 25% of their earnings. So in this case, it is telling you how much of the whole does this group account for. So our next thing is going to be our cumulative frequency. So cumulative frequency is just, you take your frequencies, your first cumulative frequency is always going to be the same as your frequency. And the cumulative frequency is just, you take the frequency of the group you're in plus all of the prior frequencies. So the first one is always the same as our frequency because we have no prior frequencies. So now we go to our second group. It's going to be 6 plus our prior frequency of 2 gives us a cumulative frequency of 8. Now we go to group 3. 7 plus 8 gives us 15. Then we go to our last one. 5 plus 15 is 20. Now there's another place you can always check yourself, because this cumulative frequency should always sum up to the total of your frequencies. Now, you might wonder, okay, going back to my quarterly earnings, what does this represent? Well, this represents how much money you've made up to that point, going off the same example. So in the first quarter, they earned $2 million. By the second quarter, they had earned $8 million because they earned $2 million in the first quarter, $6 million in the second quarter, for a total of $8 million. The third quarter, they made, up to that point, they made $15 million. So 2 in the first quarter, 6 in the second quarter, 7 in the third quarter, adding up to a total of $15 million earned by the third quarter. So this is what the cumulative frequency represents. Now, one thing I want to point out when you're doing cumulative frequency and cumulative relative frequency is these are non-decreasing values. So what does that mean, non-decreasing? So a lot of people will say that they're increasing, right? Because it's always accumulating, it's getting bigger. But it's actually non-decreasing because I could actually have an interval in here which has a frequency of 0, meaning when I go to my next interval, that my cumulative frequency does not increase. It stays the same. So non-increasing means that it will never decrease. So when I'm going from one group to the next, it only has 2 possibilities. Either the value goes up or it stays the same. It will never go down, because basically your cumulative frequency should always look like it's going up or staying the same. It can never go back down. Whereas in a frequency, it can be up or down because it's based on how much are in that group. Same thing with a relative frequency. Because if I graph my histogram, all I have to do to do the relative frequency histogram is change the scale, right? So I could easily change this to a relative frequency histogram and make this 10%. This could be, so let's say this is 40%, this is 60%, and this is 80% or something like that. In which case, or no, actually, sorry, that's not right. I did my scale wrong. But the idea would be that this would be based on the percentage. So if I look at my relative frequency, the first one was 10%. The second one was 30%, so this would be 10, 20, 30, 40. And see, so it actually looks exactly the same, except for my y-axis has changed because now this is a relative frequency. This accounts for 10%, 30%, 40%. If I wanted to graph my cumulative frequency histogram, it would basically be the same idea, except for, right, I'm going to have my intervals here. Except for now, what it's going to do is it's going to go from 2, 8, 15 to 20. So I'm going to do something like, let's say I have 5, 10, 15, 20. So for my first interval, it goes up to 2. So it'd be something like this. Second one goes up to 8. Third group goes up to 15. And fourth group goes up to 20. So this would be something like what a cumulative frequency histogram looks like. Okay, so the last one is cumulative relative frequency. Now, this one is basically the idea of your relative frequency on your cumulative frequency. So there's two ways you can do this. The first is you could take your cumulative frequency and you could find it just like you did the relative frequency. You can take 2 divided by 20, and then if you want it as a percentage, times 100. So in this case, it would be still 10%. And then this next one, we could say, okay, well, my cumulative frequency for the second group is 8. 8 over 20 gives me 40%. 15 over 20 gives me 75%. And 20 over 20 gives me 100%. Which again, you could check yourself here because this final point should always be equal to either 1 or 100% based on whether you're using decimal or percentage. Now, I told you there were two ways you could do it. The other way you could do it is you could just add up and take the cumulative of your relative frequency. So the first one, 10%. Second one, 10% plus 30% gives us 40%. Third one, 35% plus that 40% gives us 75%. And then 75% plus 25% gives us 100%. So now with this table, we could now graph all of the different types of histograms that I've brought up. We could do a frequency histogram by putting either our class boundaries or our midpoints, and then we could have our y-axis be our frequency. We could do a relative frequency histogram by changing the scale on the y-axis and putting relative frequencies. We could do a cumulative frequency histogram by our y-axis being scaled to the cumulative frequency and then doing adding those as your bars. Or we could do a cumulative relative frequency histogram, which would then, again, your y-axis would change. So notice our x-axis never changed in this, which is why when I rewrote this table, I didn't start by putting the frequency, because you don't need the frequency until you're actually trying to figure out the things doing with your frequencies. This x-axis is based on just your class intervals, and from that, in your tolerance, you can figure out your midpoint, your lower class boundaries, and your upper class boundaries. One last thing I want to say before this lesson ends is that just like when we went from histogram, or a frequency histogram, to a relative frequency histogram, where they're basically the same graph, but the scaling on the y-axis is different, cumulative frequency to cumulative relative frequency is the same way. I could change the scale of this y-axis, and it would be the same basic graph, just with cumulative relative frequency scaling on the left side. And if you do a cumulative relative frequency histogram, it should always end at 1 or 100%. So, for example, if I did something like this, if I were to change that scale, this would be something like, so this would be, I'm just going to put these as 25%. So 25%, 50%, 75%, 100%. And then boom, I've got cumulative relative frequency histogram just by changing the scale of my cumulative frequency histogram. So at this point, you have all the tools that you need to be able to take the data or take a partially filled out table, to completely fill it out, and then either create a histogram, a relative frequency histogram, a cumulative frequency histogram, or a cumulative relative frequency histogram. So in the next video, we're going to do some examples.
Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.